Look up at the night sky tonight. Every single point of light you can see is a star, and every single one of them is dying. Not quickly, not in any way you could ever watch in a human lifetime, but dying nonetheless, burning through the fuel that keeps them alive, moving steadily toward an end that was written into them the moment they were born. Our own sun has about 5 billion years left. Some stars will last far longer, but eventually, every star in the observable universe will go dark, and when the last one finally dies, the universe will enter a darkness it has never known before. So what will that last star look like? How long will it survive? And what happens to the universe after it's gone? To understand the last star, we first need to understand how stars die, because not all stars die the same way. The most massive stars burn the brightest and die the fastest. A star 20 times the mass of our sun might live for only 10 million years before exploding in a supernova, one of the most violent events in the universe. That explosion scatters heavy elements across space, seeds new star formation, and leaves behind either a neutron star or a black hole. Mid-sized stars like our sun live longer, billions of years. When their hydrogen fuel runs out, they expand into red giants, then shed their outer layers as a planetary nebula, leaving behind a dense, slowly cooling remnant called a white dwarf. But the smallest stars, the faint red cool ones called red dwarfs, live the longest of all, far longer than any other type of star, and it is one of them that will be the last star standing when everything else has gone dark. Let's trace the timeline of how we get to that final star. Phase 1. The age of stars we live in now. We currently live in what cosmologists call the stelliferous era, the age of stars. It began about 200 million years after the Big Bang, when the first stars ignited from clouds of hydrogen and helium, and it will last for another few trillion years before star formation becomes impossible. During this era, stars are born, live, and die in cycles. The gas and dust ejected when massive stars explode feeds the formation of new stars. The universe is continuously recycling its material, building new generations of stars from the remnants of old ones. Phase 2. Star formation ends, but this recycling cannot go on forever. Every time a star forms and burns and dies, some of the raw material is locked away, trapped inside white dwarfs, neutron stars, and black holes that can no longer contribute to new star formation. Slowly, over trillions of years, the supply of free gas available to form new stars decreases. Cosmologists estimate that star formation will essentially cease after about 100 trillion years. The last new stars will have already formed. No new ones will follow. Phase 3. The surviving red dwarfs. What remains after star formation ends will be the red dwarfs, the smallest, faintest, most fuel-efficient stars in the universe. Red dwarfs burn so slowly and so coolly that they can sustain nuclear fusion for extraordinary lengths of time. A red dwarf with about 8% of the sun's mass, the smallest type capable of sustaining fusion, could potentially burn for 10 trillion years. Some estimates suggest the longest-lived red dwarfs could survive for up to 100 trillion years. As the universe ages and all other stars die out, the red dwarfs will remain dim, red, barely visible against the growing darkness, but still burning. Phase 4. The last star, the very last star, will be a red dwarf, the smallest possible stellar object still capable of nuclear fusion. Alone in an increasingly dark and cold universe, surrounded by the dead remnants of everything that came before, white dwarfs, neutron stars, black holes, it will continue to burn, not brightly, not dramatically. It will glow with a deep red light so faint that, compared to our sun, it would seem almost like an ember. But by the standards of what remains, it will be the last source of stellar light in the universe. Here's where the science reveals something genuinely profound about this last star. Red dwarfs survive so long for a specific physical reason. They are fully convective. In stars like our sun, only the core undergoes nuclear fusion. The rest of the star's material doesn't mix with the core. The fusion zone is essentially isolated from the outer layers. This means the sun can only use the hydrogen in its core as fuel. When that core hydrogen runs out, the sun's fusion stops. Red dwarfs are different. Their small size and lower temperatures create a fully convective interior, meaning the entire star circulates like a slow-moving liquid, mixing itself continuously. Fresh hydrogen from the outer layers is constantly being carried into the core. The fuel is never isolated. The red dwarf uses nearly all of its hydrogen, not just the fraction in its core. This is why red dwarfs live so extraordinarily long. They are extraordinarily efficient. They waste almost nothing. As a red dwarf ages over trillions of years, something interesting happens to its appearance. It doesn't expand into a red giant the way the sun will. Instead, it slowly gets hotter and bluer as it burns through its remaining hydrogen. The very oldest red dwarfs, near the end of their lives, may actually appear blue, turning from red to blue over hundreds of billions of years, a transformation so slow it is essentially impossible to observe in real time. But here is the twist that makes this story even stranger. The last star in the universe will not die in a dramatic explosion. No supernova, no planetary nebula, no blinding final flash of light. When the last red dwarf finally exhausts its hydrogen, after perhaps 100 trillion years of quiet burning, it will simply fade. It will become a black dwarf. A cold, dark, inert ball of matter, no longer fusing anything, radiating no light, slowly cooling toward the temperature of the surrounding universe. Except, and here is the deeper twist, no black dwarf has ever existed yet. The universe is currently only about 13.8 billion years old. The shortest-lived red dwarfs would need far longer than the current age of the universe to reach their end. The universe has not yet been alive long enough for any star to have become a black dwarf. Every black dwarf that will ever exist is still a red dwarf today, still burning, waiting for a future the universe hasn't reached yet. So picture the universe at its end, not its beginning. 100 trillion years from now, the Milky Way has long since merged with other galaxies. The stars you know, Sirius, Betelgeuse, even our own sun, are gone. Their remnants are dark and cold. The universe has been expanding for so long that most galaxies are now so far away that their light can never reach us. The observable universe is mostly darkness, and somewhere in that darkness, a single red dwarf, small, dim, deep red, is still burning. Its light reaches nowhere significant. There is nothing nearby to illuminate. No planets warm enough for liquid water. No complex chemistry. No observers. It burns because that is what it does. Because the physics written into it at its birth has not yet run its course. And then, after one final trillion-year stretch, it stops. The hydrogen is gone. The fusion ceases. The last light in the stellar universe, not with a bang, not with a flash, simply goes out. Here's the thought that should stay with you. We live in what, by cosmic standards, is the brightest and most active era the universe will ever know. The night sky is crowded with stars. New ones are still forming. The universe is in the middle of its most luminous chapter. That chapter will end. And the last chapter, the long, quiet darkness after the final star dies, will last incomparably longer than everything that came before it. The era of stars, the entire period from the first star to the last, is just a brief, brilliant opening act in a story that continues for far, far longer in the dark. But right now, tonight, you are alive during the lights. Look up.